Welcome to the course on advanced power electronics. So today we'll cover the topic vector control of synchronous motor drive. So the vector control method control the speed through magnitude and phase of AC excitation, and the vector control of current and voltage results in control of spectral orientation of the electromagnetic field in the machine, and it is therefore referred as a field oriented control also. And the static quantity flux, current, voltage are resolved into direct and quadrature axis component which rotates in synchronous with the rotor. So direct and quadrature axis component are the quantity which are aligned along and perpendicular to the field winding axis respectively. Therefore, DQ axis component, the position of rotor flux is required continuously, and the vector control makes a synchronous motor drive equivalent to a DC motor drive with superior dynamic performance. So based on the DC machine concept, the requirement of torque control can be outlined as follows: an independent control of armature current to overcome the effect of armature resistance, leakage reactance and induced voltage, and field flux may be constant value also, an orthogonal spectral angle between the flux axis and MF axis to avoid the interaction of MF and flux. Therefore, if all the three requirements are met at every instant of time, the torque will instantaneously follow the current, and torque control will result. And the current source inverter driven synchronous motor is the best candidate for vector control, because in a CSI current can be controlled in amplitude and phase both, and the field winding of the motor is physically available and field can be controlled as a in DC machine. Now coming to DQ modeling, which is the base, you can call it the backbone of the vector control. So coming to the introduction to this DQ model, in the basic two-phase representation of synchronous machine, the axis of north pole is called direct axis or D axis, and the quadrature or Q axis is defined in the direction of 90-degree electrical ahead of the direct axis. Under no load operation with only field excitation, the field MF will be along with the D axis and the stator indoor voltage will be along Q axis. And this is typically the spectral representation of your synchronous machine. I mean, you can just have a look or with the permanent or field excitation. Normally, we are considering conventional synchronous machine which have a field excitation on direct axis, and then you have a damper winding also, I mean, for the dynamics. So the voltage of any three-phase system can be viewed a single vector in three-dimensional space. When the sum of the three voltage add to 0, the voltage vector then rotates on a plane, that is DQ plane, and the rotor windings F, D and Q are already aligned along with the D and Q axis. So the mathematical description or model is based on the concept of an ideal synchronous machine with two basic poles, and the fields produced by the winding currents are assumed to be sinusoidally distributed around the air gap. And the main aim of the DQ model is to eliminate the dependence of inductances on rotor position, and to do so, the system of coordinates should be attached to the machine part, and that has a magnetic saliency on the rotor for the synchronous machine. So DQ model should express both stator and rotor equations in rotor coordinates along with the rotor DQ axis, and hence there is no coupling between the two orthogonal axes, and Park equation form the basic for the analysis of operating mode of synchronous machine. And when the three-phase voltage form a balanced sinusoidal three-phase set, then the voltage vector has a constant amplitude and therefore traces out a circle in a DQ plane. When the D and Q axis of the DQ plane are made to rotate with the voltage vector itself, the projection of the voltage vector on the DQ plane has been shown to become constant, as you can see typically here in the phasor diagram as well as physical representation of the machine. And this is typically the inductance matrix. If we take a matrix for ideal silent pole machines, I mean, it has a typically we have a on stator three-phase, and rotor we consider of course the field winding and D axis damper and Q axis damper, and then that makes the element 36 element between 6. I mean, typically you can call it electrical circuits on stator and rotor. And this is where we can define LA, and that L as sigma leakage plus L0 plus L2 cos theta. Similarly for your AB, minus half L0 L2 cos theta 2 minus pi by 3, LAC minus half LO plus L2 cos 2 theta plus 2 by 3, that's also becomes LCA, and LF is M S of cos theta, that is LFL, and ADR is M SD cos theta, that is LDRA, and LAQR is a minus FQ sin theta, that is LQR. So LBB will be L S sigma plus L0 plus L2 cos theta 2 theta by 2 theta plus 2 pi by 3. And similarly LBC half minus half L0 plus L2 cos 2 theta LC equal to LCB LBF MS cos theta minus 2 pi by 3 LPF M, and LBDR MSD cos theta minus 2 pi by 3, that is LDRB, and LBR equal to minus LBQR equal to minus MSQ sin theta minus 2 pi by 3, and LCC equal to L delta sigma plus L0 plus L2 cos theta 2 pi by 3 minus 2 theta minus 2 pi by 3, and CF equal to MSF cos theta plus 2 pi by 3, and LCDR equal to MSD cos theta plus 2 pi by 3, and CQR equal to minus MSQ s theta 2 pi by 3, and LFF is LF sigma plus LFM, LFDR equal to MSD equal to LDR, and LFQR is 0, LDR equal to LDR sigma plus LDR, and LFQR equal to 0, and LQR equal to LQR sigma plus LQRM. So this all these 36 inductions. Then we have a volt ampere equation in page variable. V matrix equal to Ri plus T upon dt lambda, where V the vector, VF, and 0 volt is applied to the damper, both 0 0, I equal to I B IC, IF, and 0 0 under steady state, and lambda equal to lambda A lambda B lambda C lambda 0 0, and then V becomes equal to Ri plus L Ti upon dt I plus I dl upon d theta L into d theta upon dt, and torque equation is T equal to P by 2 I transpose dt upon dt L into I. Now the stator is current space phasor in stator coordinate is dash station 2 by 3 in bracket IA plus AIB plus A square IC, and phase A flux linkage lambda equal to LAIA plus LABIB plus ACIC plus LAFIF LDR IDR L plus LAQR IQR, and using the inductance matrix can be written as lambda A equal to LA sigma real part of IS plus 3 by 2 LO real part of IS plus 3 by 2 L2 real part of IS e to power 2 J theta plus LAF real part IF e to power J theta plus LADR real part of IDR e to power J theta minus real part in bracket J LDR IQR e to power J theta. And the stator flux vector in station goes same, lambda SS equal to by 3 in bracket lambda plus A lambda B plus A square lambda C, using lambda A lambda B lambda C, lambda S equal to L sigma delta IS plus L 3 by 2 L0 IS plus 3 by 2 L2 IS e to power 2 J theta plus LF IF e to power J theta plus LADR IDR e to power J theta plus J LADR IQR e to power. Alternately, it can be written also lambda is equal to lambda S e to power minus J theta, and IS equal to IS F e to power minus J theta, and IS equal to ID plus J IQ, and lambda is equal to lambda D plus J lambda Q. And the volt ampere expression DQ variable VD equal to RS ID plus G lambda upon TD, that minus omega R lambda Q, that is speed voltage, and VQ equal to RS IQ plus T lambda Q upon DT plus omega R and lambda D. And torque developed by the synchronous motor is T equal to 3 by 2 P in bracket lambda D IQ minus lambda Q ID, and the DQ variable and phase variable are related to VDQ 0 equal to P theta VABC, and VABC equal to P theta transpose VDQ 0. And mathematically, the voltage in terms of DQ variables, VD equal to root 2 V cos theta 0 and VQ equal to root 3 V sin theta 0. And this is the signal flow diagram of the synchronous model. I mean, your input are typically VF and VD, and it's going to different blocks to find out the finally your IF, ID, and lambda D, IQ. And similarly for the your Q axis phasor diagram, signal phasor diagram, and this is for signal flow diagram, of course, with lambda 2 to typically get the speed and your position with the of course developed torque and minus load torque, and then mechanical part of it like. So now coming to vector control. So the synchronous motors have either electromagnetic excitation palm magnets on the rotors. Their rotor for analysis, a high energy palm magnet may be replaced by a fictitious winding carrying a constant field current, and the input quantity of the synchronous machine shall be stator flux lambda S star, the field excitation current IE star, and the electromagnetic torque T star. However, because of the field current is adjusted to a predetermined value according to a given power factor, the input to the machine reduced to only 2. For generally, the case of silent pole field excited synchronous motor in stereo flux orientation is considered, and synchronous machine equations can be summarized at Vs equal to Rs Is plus P lambda s plus J omega R lambda s, and lambda s equal to lambda d plus J lambda q. And this is typically the phasor diagram of synchronous under transient conditions. I mean different D and Q axis and all the volt ampere typically relation here. And here in lambda d equal to LST ID plus MD in bracket IF plus ID plus ID capital D, I capital D, and lambda q equal to LS sigma IQ MQ in bracket IQ plus IQ capital, and T equal to 3 by 2 P real part of J lambda S IS star equal to 3 by 2 P lambda in bracket lambda D IQ minus lambda Q ID, and then RD plus P lambda Q into ID equal to minus MD P in bracket small I small d plus IF plus I capital D, and RQ plus P LQ into IQ equal to minus MP P in bracket IQ plus IQ capital, and RF plus P LQ into IF minus VF equal to minus MD P in bracket ID plus IF plus ID capital, and from this ID capital is minus MD in bracket IF plus ID into P divided by RD plus P MD plus LD delta, and IQ equal to minus MQ IQ P upon RQ plus P in bracket MQ plus LQ delta, and lambda D equal to LQ LS QRD plus RD plus P L lambda delta into LD IF plus ID divided by RD plus P MD plus L D lambda Q, and L lambda Q equal to LS delta IQ plus RQ plus P LQ delta into MQ divided by RQ plus P in bracket MQ plus LQ delta, and T star equal to 3 by 2 P lambda star IT star, and I equal to star equal to T star divided by lambda S star into 2 by 3 P, where IT star is the torque producing reference current, and with this IM star equal to IT star 10 gamma star, and IS star equal to IT star and sec gamma star, and ID upon IS star equal to sine in bracket minus gamma plus delta, and IQ upon IS star equal to cos minus in bracket minus gamma star plus delta, hence IM star is the field producing reference current. So coming to control strategy, from the equations derived earlier, two representative control strategy are considered: variable gamma mode and in bracket ID equal to 0 or ID equal to not 0, that is minus delta plus gamma plus delta equal to constant, and constant gamma control equal in bracket or gamma star equal to 0 or unity or leading power factor. And variable gamma control, so variable gamma control, that is 0 ID is used for surface PM machines up to base speed, and then the cycle not wide field excitation up to 5% of rated speed with IF constant. And in the case of interior permanent machine, ID may be non-zero or negative at 0 speed, or in order to utilize reluctance torque, since LD is much smaller than LQ. So now coming to in this case variable gamma control, gamma star and the stereo flux lambda S star both vary and can be calculated from following equation, keeping ID equal to 0. T star equal to 3 by 2 PM ID IF IQ star equal to 2 T star upon 3 PMD IF star, and sin gamma star equal to LQ IQ upon lambda H star, and lambda star equal to under root MD IF star square plus LQ IQ star square. And this is the typically synchronous machine current decoupling network for stator flux orientation, where all the blocks are properly explained, like. And the torque given by following equation, ID not equal to 0, so T equal to 3 by 2 PM ID IF IQ plus 3 by 2 P in bracket LD minus LQ into ID star into IQ star, and the stator flux for maximum torque is given lambda S star equal to under root MD IF star plus LQ LD ID square plus LQ IQ star square. And constant gamma control for unity power factor, gamma star equal to 0 is a typical value for cyclic flat synchronous for leading power factor, gamma star equal to minus 7 to 8 degree constant in a typical force current source inverter flat synchronous machine. So vector control of synchronous motor can be executed by control of any one vector, current vector, voltage vector, or torque vector. So it consists of current decoupling network and the current vector rotator that generates the reference phase current, and the position of stator flux or stator current vector is obtained from reference torque, flux, and or gamma star, and that gamma star is constant. Therefore, this control is known as indirect or feed-forward vector control. The position of stator flux or current is obtained through an estimator or indirect vector control. And this is typically indirect vector control. So we have a lambda star, gamma star, and T star is coming from the control, and we get IM star, IT star, and delta, and from theta adding it, then we get the typically your angle, and with this all four input we get typically IA star, IB star, IC star from this current vector rotator. This is for constant gamma control because we don't then. And this is a phase diagram for this vector control, how it is the relation are there derived, and this is your variable gamma control where T star, IF star, and omega star u, and we get ID star, IQ star, and from ID IQ and theta r we get the value IA, IB, IC star, and this is the phasor diagram corresponding to this relation. And this is the direct vector control where we have a typical gamma star, lambda and T star, and we get IF, IA, IB, IC for the control, like from the relation. So the voltage vector of synchronous machine uses decoupling of vector, and equations for use in vector control are VR is equal to RS P lambda s plus J omega R lambda s, where lambda s equal to lambda s, and VM equal to RS IM plus P lambda s, and VT equal to RS IT plus omega R lambda s, and decoupling voltage vector are VD equal to RS ID plus P lambda D minus omega R LQ lambda Q, and VQ equal to RS IQ plus P lambda Q plus omega R lambda D. So the voltage vector decoupling may be applied to indirect or direct control with gamma star constant or gamma variability in DQ control. So since the current decoupling network is complex for indirect control and lambda star constant, voltage control is applied in the direct approach. So in the combined voltage and current vector control, the current control prevails a low speed, and at high speed voltage control takes over, and the direct approach includes the sum machine parameter in the flux calculator only. So in the indirect method, the machine parameters are used in the reference current calculator and in voltage decoupler both. And the block diagram, the next slide shows the combined voltage and current vector. So you can clearly see direct stator flux for constant gamma control, and you are able to get from flux and lambda gamma star and T star. We are able to get IF, and typically we see for the control of the motor and the respective feedback for the calculator. This with variable gamma control. Again, we go with the torque and calculate ID and current control. We get the voltage applied to the field of them, and this is the phasor diagram corresponding to that. So the hysteretic current is entirely Q-axis current with the field orientation. The axis between the E and IA, that is gamma equal to 0. Absolute rotor position from sensor is directly utilized to set gamma equal to 0 by controlling the inverter firing. And because of the commutation delay inherent in current source inverter, the sum of the compensation is necessary to maintain gamma at 0 for different levels of current and different level of operating frequency. So there can be another method which uses current regulated pendulum inverter in the field under control and uses absolute rotor position information to generate IQS star and IDS star command, and field orientation is obtained by simply setting IDS equal to 0. And this is typically current regulated field under control. So we have a torque command and field current command, reference current, and we have a positions, and then we get a reference current or current regulated pendulum voltage source inverter, and field current we control separately. So the choice is for the value of IDS star that 0 can be there. There is a motor power factor or other performance features are to control. The IQ star and ID star commands in the rotor reference frame are converted into stationary. Stator reference frame is IQD S star equal to EJ theta R IQDS star, and the two phase stator current commands can be converted to 3-phase current I star equal to IQS star cos theta plus ID star sin theta. Similarly, for IB star and IC star, you can calculate from this relation. And then, of course, you can calculate from typically for magnitude angle resolver. So you have IQS and IDS, from which you can have IQS amplitude is under root of ID square plus IQS square, and angle tan inverse IQS upon IDS. So the use of resolver takes IDS and IQS as input, and the magnitude output of resolver will become current command for current source inverse. The combined theta R and pi signals will set the phase of the current vector IQD is in the rotor reference frame. So the angle output of the resolver will become as gamma command and will be fed to phase regulator to be combined with the rotor position information. Now coming to novel vector control for synchronous motor drive via dynamic modeling. So vector control dynamic, so design strategy inverse dynamic modeling. The block diagram shows the design concept. So we go with the torque command, plug command. Then we go for vector controller, go to current controller and converter. Output current goes to the synchronous motor, and from which we get the torque and plug for the feedback for inverse dynamic. And to the Q axis and D axis fluxes which correspond to the torque command are flux commanded are obtained pi Q star equal to RKQ upon S plus LKQ divided by 1 plus S up 1 plus M upon MQ in bracket RKQ over sub plus LKQ into IQ star plus LA into IQ, and pi D star equal to under root pi S square plus pi Q square. So the field-oriented command can be written IF star equal to 1 upon MQ in bracket pi D star minus LAID star plus S upon RKD divided by 1 plus S upon RKD in LKD in bracket pi D star minus LAID star minus ID star. And this is typically the block diagram. The failure portion of vector control, what is the end portion of the synchronous machine is emulated to typically in the complete diagram. And this is the system configuration for speed control. We have a reference speed, feedback speed, and we from speed, actual speed, we get the flux, and the speed control gives the torque. With this, we convert into virtually the ID, IQ, and field current. And field current is regulated by the another converter. And from three-phase sense current, we have ID, IQ calculation from position. And then we have a current controller for cycle converter drive. And these are typically a simulated response of the speed control, how real D axis and Q axis current looks like during starting, then reversal, and steady state running. And this is typically the terminal voltage, and typically field current and terminal voltage. And these are typically the exponential response in terms of your IQ, and typically the speed. And this is the field current and phase voltage. So now coming to topology of synchronous motor drive. So this is typically VSI fed. Typically VSI is 6 pulse rectifier, and this is another VSI with the 12 pulse rectifier just to improve the quality and reducing the harmonic in the grid for a high rating because GTR. And then with the 18 pulse converter on the rectifier side, control convert, and then the 24 pulse converter on the input side to reduce the harmonic. Is a control block diagram typically for vector control complete drive, how really the different signal for lambda S, gamma Q, and T star is you get a field reference current as well as your ID, IQ, and then you have a voltage controller typically in this your VSI control converter. These are with current source converter with the 6 pulse rectifier and 12 pulse rectifier with current source inverter, and then you have 18 pulse with 18 pulse control rectifier with current source inverter. Current source inverter is 24 pulse rectifier, and this CSI fed of course for vector control. So you again have input same lambda star, gamma star, and T star, and from which you calculate the typically reference current for control of the current source and field current control. So this is typically 18 switch cycle converter which have been in practice for long for large rating synchronous motor. You can go up to 1/3 frequency, and this is another your 18 switch load commutator cycle converter we already covered in the previously, and this is your 36 pulse switch real cycle converter. You can go up to 2/3 frequency. This is 72 switch cycle converter which you can go even up to the input frequency for the control. And they typically cycle converter drive control that you have reference speed from which you are getting reference flux, and you are getting torque producing component, and from flux you are able to get typically from for field excitation, and feedback you come for the magnetic current, and with the sense current you are able to get a VT and VM, and then that you convert from cos alpha and sin alpha into A star B, B star B, C star for cycle converter for the purpose of generating the control signal. And this is typically the matrix converter, and this is how the matrix converter control in a back control main in the same way as we do in the previous case. So now coming to sensorless synchronous motor drive. So in the past few years, the great efforts have been made to introduce speed or shaft position sensorless torque control, vector control, torque control drive, and these drives are usually referred as sensorless drive. Although the terminology sensorless refers to only the speed and shaft sensor, there is still some other sensors in the drive system that is current and current sensor. The use of encoder or jailbur on the machine shaft may undesirable due to the cost or reliability. So therefore, the extraction of rotor position, more specifically rotor flux position information, may be carried out from electrical signal measurement, and sensorless method requires fast and accurate signal processing methods and processor to obtain the various information as and when desired. So coming in, sensorless vector control drive have become the norm of industry, and almost every large manufacturer control technique like PLC, Siemens, Hitachi, Yakagawa, European Therm has introduced sensorless method for various motors. However, it is a main features of almost all the additional industry that they cannot operate at very low frequency without speed or position sensor. So in general, to solve the problem which occur in low frequency, a number of special techniques have also been proposed by various investigators to reduce the total hardware complexity and cost, to increase the mechanical robustness and reliability of the drive, and to obtain the increased noise amenity. It is able to eliminate these sensors in vector control and direct torque control drive. So further, an electromechanical sensor increases the system inertia, which is undesirable in high performance drives, and also increases the maintenance requirement. So now coming to topology of sensorless control of synchronous motor drive. So we have here the typically ABS fetching sensorless control with the voltage control, vector control. We have a speed feedback and speed sensor. The speed we are estimating from voltage and current, and then position also, and then speed controller gives the torque, and if actual estimated speed gives the flux, and that we convert into ID, IQ, IF star, and which we regulate with the help of controller in the VSI as well as the thyristor converter for field control. And these are the voltage vector of synchronous motor uses decoupling of voltage vector, and the equation used in voltage vector may be VS star equal to IS RSIS to plus V lambda plus J omega lambda where lambda is equal, and VM equal to RSIM T plus P lambda s, and VT equal to RS IT plus omega R lambda s, and decoupled voltage R PD equal to RSID plus P lambda D minus omega R LQ, and VQ equal to RSIQ plus P lambda Q plus omega lambda D. So all variables in the rotor reference frame, the flux linkage are related to the currents in the different windings with reference to the D and Q axis variables, and can be done lambda Q equal to LS IQ plus LMQ LM IF2, lambda D equal to LS ID plus LM IF1, and lambda F1 equal to LF1 IF1 plus lambda M ID, and stator flux lambda star and the torque command T can be calculated from the following equation, keeping ID equal to 0, T star equal to 3 by 2 PMD IF star, and ID IQ star equal to 2 T star upon 3 PMD IF star, and sin gamma star equal to LQ IQ upon lambda S star, lambda star equal to under root MD IF square plus LQ IQ star square. So the field current command can be written as IF star equal to 1 upon M Q in bracket phi D star minus LA ID plus S upon RKD upon 1 plus S RKD LKD bracket of phi D star minus LA ID star minus ID star. So for sensorless, the estimation of position or speed becoming inevitable. The speed can be estimated by following relation: omega equal to in bracket lambda E beta minus lambda beta E alpha divided by lambda square equal to lambda alpha square plus lambda beta square. The angular flux lambda equal to tan inverse lambda beta upon lambda alpha, and the stator flux is estimated from motor back EMF by using the integration can be expressed E equal to lambda upon dt, and motor back EMF can be written equal to Vs minus your RSIS, and this is the typically the you can call it current source inverter fed synchronous back control of synchronous motor type. We have a reference speed, we have estimated speed controller which gives the torque, and then we have a how much speed flux and flux torque. We go to the block back control, so we get IDIQ IF star, which go to the of course field controller converter, and for of course for the motor we have a I alpha I beta position for the ID star IQ star we convert, and from clock we get IB IABIC. So taking IBIC, we just do the switching for the inverter. This is typically cycle fed drive. We can easily implement the way we have, and this is the control block of cycle converter fed drive, like same block of, except we derive the reference voltage for control of cycle converter. This is typically the matrix converter. How really we go ahead again for the voltage vector and decide the duty cycle control. Now coming to sensorless control of CSI fed synchronous motor drive. The GTO based pendulum current source inverter drive has been increasing use in high power application because of its simple structure and sensor output current, and the dynamic response performance of a CSI drive can be considerably improved by employing field control method. In the field control method, the accurate estimation of the motor flux is a critical task. So there are two basic flux estimation models: voltage model, current model. And current model require either motor speed or the position information, so not useful for sensorless method. And the voltage method model is a much simple and requires only the motor terminal volt quantity, is uses in integer to drive the flux. So the motor torque and flux should be controlled independently. The motor flux can be adjusted by the rotor excitation winding, and the magnetizing component of stator current IM is kept 0. While M equal to 0, the motor torque will be proportional to the stator current IT and similar to a DC machine. And the current torque current reference can be as IT star equal to 4 by 3P T star upon lambda star, and capacitor current circle root IMC star equal to minus omega C UT, and IT C star equal to omega C UM. And these are typically the block diagram current source in your back control drive. So we of course have a from current reference, and we have a typically a DC link current also to drive the current sensor with power feedback and sensorless mode. And this is the stator flux estimation how can be converted from back EMF, like, and this the EMF can be obtained from the stator voltage vector. So EMF equal to US minus RIS, and the flux magnitude angle are calculated lambda equal to lambda is under root lambda alpha square plus lambda beta, and phi equal to tan inverse lambda alpha upon lambda beta. And the motor speed can be derived from the estimated flux omega estimate equal to in bracket lambda alpha into EMF beta minus lambda beta into EMF alpha divided by your gamma delta square, the lambda square. And this is the response motor voltage current and estimated flux when the motor runs at 0.5 very low speed, like. And this is transient response to step reversal from 10 Hz to minus 10 Hz. You can clearly see how the voltage as well as the current and position changes. This is for when the motor current, typically for the case of starting. So coming to self-sensing control of wound rotor sensorless synchronous motor drive. So the present sensorless rotor position estimation utilizes the natural AC component for the rotor field oriented excitation, and the phase lock loop and external Kalman filter both requires. Both techniques are able to estimate the rotor position and magnitude polarity. However, the Kalman filter offers a faster convergence and a higher accuracy, and it is able to provide the reliable rotor position estimation in the whole speed range of the drive. So mining horse drive operates at relatively low speeds, typically from 0 to up to rotor mechanical speed of 1 Hz, and thus the back EMF based technique cannot be used. However, one high frequency signal is naturally present in the drive, and it is the AC component of the rotor field excitation current generated by the bridge rectifier supplying the rotor circuit, and this component is a non-sinusoidal signal with a frequency of 300 Hz. So this method proposes to use this signal to estimate the rotor position. The motor will be used as a rotor position sensor, and the behavior of which is reminiscent of the visual one. So now coming to sensorless estimation of rotor position, the rotor of the wound rotor synchronous motor is fed by DC flux excitation current, which is necessary for excitation of the magnetic field inside the motor. And due to the feeding the rotor from three-phase bridge rectifier, the rotor current inherently includes the AC component of high frequency, and this AC component of rotor excitation current can be used as a natural induction signal. It can be used for estimation of the rotor position without the sensor on the shaft. So the model of stator winding in the resolving reference DQ link the rotor flux linkage vector Ust equal to RSI IST minus omega R pi SQ plus D upon dt pi SD, and USQ equal to RS pi SQ plus omega R pi ST plus D upon dt of pi SQ. So DQ component of the flux linkage vector is pi SD equal to LSD into IST plus LMD to IF, and pi SQ equal to LSQ plus into ISQ. The high frequency component of stator current vector in alpha beta reference frame are determined by conventional Planck transformation. So IS alpha I, IS beta I, equal cos theta r sin minus sin theta and sin theta r and cos theta r into IS di and 0. Similarly, IS alpha I, IS beta I equal to Ki, K into I Ri in bracket cos theta cos phi I and sin phi r, that is K equal to minus lambda MD LMD upon LST into KRI, where Ri is the high frequency component of the rotor field excitation IR, and this is typically the high frequency component of rotor current IRI and its response in the alpha beta reference frame. Now coming to extended Kalman filter. So this estimator is closely related to the Kalman filter designed for estimator of rotor position from resolver, and the three different key differences are the state variable approach is formed only by the rotor position, and the observation equation is multiplied by the observed excitation signal. The reason for first difference is the signal of a rotor excitation is noisy, yielding a unsuitable speed estimate for feedback, and therefore we estimate the speed from the estimated position using a numerical derivation on the fixed length window. And the second difference results in a time varying Kalman gate. This is advantageous because its reduces is sensitive to the measurement noise. And assume that the measurement of the stator current is degraded by the Gaussian noise as follows: IS alpha I is beta I equal to KRI RI into cos your psi r and sin r plus beta y. The rotor position will be considered to be only state variable with dynamic equation given as psi r k equal to VR k minus 1 plus delta t omega r. To form a steady space model with the linear state equations and nonlinear observation equation, an extended Kalman filter can be applied for estimation of the state variable, and the result of the extended Kalman filter estimate is the most likely rotor position theta k, and its covariance matrix pk upon a k. And the extended Kalman filter equation can be written pk k minus 1 equal to pk minus 1 by pk minus plus q, and ry equal to ck pk fk minus 1 ck t, and r plus k equal to pk k minus p k divided by k minus 1 ck t ry minus 1, and similarly for pk equal to pk minus k minus 1 minus k ck pk minus k upon k minus 1. So with matrix ck equal to k r ri in bracket minus sin I k and k equal to minus 1, and cos v equal to k at the k minus 1. The updated estimate is vk equal to vk k minus 1 plus k I alpha I and is beta I minus k ri, where cos theta angular cos theta I cos sigma I k minus 1 and sin theta k minus 1. So now coming to phase lock loop. PLL can so interpreted as a special case of Kalman filter, but for simple state model, and PLL is most utilized and well known tool for sensorless control with high frequency injection signal, and it is an Italian of simplicity and good functionality that is commonly used in resolver estimation. And this is a PLL, how it goes with that position, and you get typically the sense current and typically estimation for the position evaluation by PLL. And this is the result of PLL, high frequency current demodulated using sine wave and cosine wave. So basic element of PLL is a PI controller and RPLL that would minimize the difference of input current ISQI from 0, and the output of PI controller correspond to the speed of drive, which varies from 0 to rated speed for the proportional drive. And it is possible to find a fixed tuning of the PI controller that will perform well in the full range of the drive operating condition. And the speed is not estimated by the Kalman filter because of the low reliability of such solution. Instead, it is estimated by numerical derivation of the estimated rotor position one time window over a 7 sampling period. So omega rk equal to vk minus 1 divided by 7 delta t. Now coming to band pass filter. So design of band pass filter has important impact on the performance of the estimator. The frequency of the AC component of the rotor current is fixed. The frequency spectrum of response in the estimator current is changing with the rotor speed, and therefore the bandwidth of the filter must be set to 2 times the maximum estimated frequency. And these are typically response of band pass filter, corrective magnitude with the blue and the phase green with the green, but for 6 other for 3 sections. And these are sensorless control of investigated noise minus drive with wound rotor cell and pole synchronous motor with all the input and estimation, and that's the reason position is not estimated here. So the fundamental control loop is the speed control loop, and thus the demanded rotor speed is controlled by PI controller, where the speed feedback is estimated by the sensorless algorithm, and the speed controller generates the demanded magnitude of the stator current vector IS, which is limited to the maximum allowed stator current IS max by the symmetrical limiter 0, 1. And this is the typical behavior of PLL estimator in higher speed. You access response and your beta axis response and estimated position and rotor position. And behavior of the extended Kalman filter based estimator at higher speed with the different signal. So now coming to modeling and sensorless control of cell and pole, one field synchronous machine initiator flux coordinate. So in field one to control, the machine is generally modeled in the flux reference frame in which the control is done, and synchronous motor model in the DQ reference frame is well defined and therefore control is straightforward. But in the most of the synchronous motor drive, the state flux oriented control is preferred compared to the DQ reference frame, and the reason are the capability to control the power factor and the possibility of optimally diminishing the stator side converter. So dynamic modeling of DQ. So questions for fluxing gauge of cylinder pole machine along with the DQ axis is your phi D S phi QS and phi alpha, that is LD 0 LMD 0 LQ 0 LMD 0 LF dash, and where all the inductance are defined. So now develop electromagnetic torque MD equal to 3 by 2 P by 2 in bracket LD minus LQ into IDS plus LM ID FD dash in bracket close and IQS. And this is the phase diagram of DQ along with the stator flux rotating axis, like with the lagging power factor, and this is with the unity power factor flux representation. And these are the equation. M equal to 2 by 3 by 2 IMS into ITS, and the derivation comes IMS equal to your LM in bracket LS divided by LM IMS plus I mu bracket close. Now coming to cylindrical wound rotor machine, the general practice is important to implement the failure control for synchronous machine in stator flux coordinate, and by forcing the stator current along with the stator voltage axis to access unit power factor operation can be achieved, and UPF operation is achieved in control by forcing stator magnetizing component IM 0. In that case, the stator flux magnitude phi s along with the M axis is maintained constant and varying IFT different value of torque angle. So reference for cylinder control IFD reference star equal to I mu reference divided by cos delta. Coming to controller design, the stator current controllers are designed using the equation stator voltage along with M and T axis. So Vms equal to Rs Ims plus d upon dt pi ms minus omega pi ds, and Vts equal to Rs Its plus d lambda upon dt pi ts plus omega ms into pi ms, and pi ms equal to constant, pi equal to pi s, and pi ts equal to 0. So Vms equal to Rs Ims and Vt equal to your Is Its and plus omega s, typically phi ms. So this is typically the current control design. So therefore a simple k pi s integral control is sufficient to hold the steady state. The bandwidth of the controller can be chosen by designing the value of its proportional gain kp. So typically salient pole construction of rotor includes the effect of saliency in flux equation. To achieve the objective of UPF operation, fast dynamics of control, the equation for IM, I reference there, IM is calculated from here, IF dash also calculated from this class. So now coming to your open loop flux observer can cause problem of DC drift at the output of indicator and also give rise to phase as well as the magnitude data, especially at low frequency. To offset these drawback, a closed loop flux observer generally used for sensorless control, and closed loop observers add error correction mechanism to the flux indication process by means of feedback control. And now coming to closed loop rotor flux observer applied to wound field synchronous motor. So estimation of the rotor position angle for stator flux stator sensorless control using the method of closed loop rotor flux observer requires an accurate rotor flux model of the wound rotor synchronous machine instantaneous coordinate as well as DQ coordinate. So the forward rotor flux integration path is implemented using the expression of rotor flux in stationary coordinate. So phi alpha t in bracket integration of V alpha s minus I Rs I alpha into dt minus LQ ID I alpha s, and V beta t equal to in bracket integration V beta s minus Rs and I beta s into dt minus LQ I beta s. And the feedback error correction variable in the magnitude of rotor flux, which can be estimated using the current model, is your phi star, typical absolute value equal to LD minus LQ into IDS plus LMD into IFD stress. So sensorless field control of in the stator coordinate requires the estimation of flux position, mu, torque angle delta, and feedback as well as feed forward term in stator coordinate. Sin delta equal to LQ ITS divided by under root LQ ITS square plus in absolute phi s minus LQ IMB square, and cos delta is equal to phi s absolute value minus LQ IMS divided by under root LD ITS square plus I phi s minus LQ IMS square. And these are the closed loop observer applied to wound rotor machine, how you are getting form voltage typically, the flux, and similarly for alpha beta axis, and then you are getting the angle, and from these currents you are able to get the typically ITSMS and all the equations. And these are response, tangent response of field controller, reference speed, estimated speed, your IF D reference, IFD into IB. These are the typically the result with ITI stator current IS1, then the ITS, and then your estimated speed and your reference speed. This is for tangent response for flux controller. So coming to direct control of the synchronous motor drive. So the direct control is a direct control of torque and flux, stator or air gap factor, which triggers either voltage or current vectors available in the inverter. This method is therefore known as direct torque and flux control of torque vector control also, and the parameter depends of this control is generally reduced as compared to the vector control. So direct control of synchronous motor drive is accomplished by speed control, reference flux generator, field current controller, and table of optimal switching for space vector model. And this is the block diagram your torque vector control, where we define the T reactive and typically T active with the proper reference speed and position. We are able to control voltage source converter with 2 level flux control and 3 level torque control. तो स्पीड कंट्रोल इक्वेशन एट द कांस्टेंट गिवन इज ओमेगा ई स्टार ओमेगा ई के इक्वल टू ओमेगा आर स्टार माइनस ओमेगा आर के इज द रेफरेंस स्पीड ओमेगा is the rotor speed and omega is the speed error. Speed control is usually proportional integral controller. The output of PI control can tk star equal to tk star minus 1 plus kp in bracket omega k minus omega k minus 1 plus ki omega k, where kp ki are the proportional integral gain of the PI control. So coming to reference flux generator, the direct control requiring flux reference, which can be calculated using the following steps: calculating the line to neutral voltage corresponding to rated flux, V equal to VA rated in bracket omega m star upon omega m rated, and calculating the reference flux corresponding to omega m star equal to m dash equal to VA upon omega m star. So DDC control the switching of the inverter directly based on the table of optimal switching, and VSI based direct torque control scheme on require reactive torque turn, and T reactive is a frequency speed dependent and used in the field current. So for perfect control, it avoids the calculation of field current from saturation dependence parameter and has a T reactive equal to 3 by 2 P Q1 upon omega E equal to 3 by 2 P in bracket real part of lambda is I. So it is also a PI control which acts as to minimize the current error in the reference field current and actual field current. The output of PI control कहते हैं VK star equal to VK star minus 1 plus KP bracket IK minus 1 plus KI KPI is the proportional integral gain of PI control. I is the current error, and this control voltage is used to generate the firing pulses of the thyristor converter feeding the field winding. So in the DDC control scheme shown, the flux reference calculation has two options: flux slash speed option for the application where the load torque is function of the speed only, pump application, and flux torque option for the application where the load torque changes with the time also, that is shape option, and both the options have to take care of below base speed and above base speed operations also. So now coming to flux estimation, the state estimation can be used for estimation of the flux from stator vector Vs equal to RSIS plus G lambda S dt, where all parameters are defined, and lambda S equal to integration Vs minus Rs RSIS into dt. Now for flux estimate, to obtain the great accuracy, improved flux estimate observer based Bloomberg-Kalman filter and artificial intelligence based technique may be used. So for torque estimation, the torque reference torque T reactive is already mentioned. For starting, can be estimated to constant value below base speed operation and from desired speed above base using T reactive equal to P star upon omega, where P is the constant power of the error of T reactive and T star reactive. T reactive is controlled by field control, the right field current control, the deviation of the speed sets as the speed control output. So switching a DC to set the switching sequence of inverter, the operating plane assumes that 360 divided into 6 sector of 60 degrees, and the voltage vector has 6 positions of the operating plane named as V1 to V6, 60 degree apart from each other, and 2 null positions at V0, V7. These vectors decide the on-off condition of the specific solid state switch as shown in the next slide. So the inverter switching sequence decided by table of optimal switching based on the operation theta 1 to theta 6, and this is the table of optimal switching. The torque is 3 level, flux is 2 level, and you have sectors of 1 to 6, and all the vectors are defined typically. So VSI based DDC, the table of optimal switching is based on the torque, mounting on braking, flux position, and sector of operation theta 1 to theta 6. For any particular hysteresis band, the voltage vector changes in direction where it touches the hysteresis boundary. The change vector shall be according to the direction of rotation. Torque and flux are increased to decrease, and if the torque is motoring, the flux touches the lower hysteresis boundary, then the vectors shall be applied such that the flux increases and vice versa. And these are typically flux overlap graph and voltage vector. How the switching decide? So last V0 and 7 are the zero vector, remaining are the active vector, and these are typical current source converter based. So here again we have a from speed control, reference feedback, speed control, torque reference, and T reactive we decide for getting the field current, and then field current is controlled from your field winding thyristor converter, and then for the motor typically for current we design the DC link current also to get reference DC link current, that's also done by thermistor converter, and CSI get typically from a torque and flux to get the typical option switching for 2L to get the switching of current source input. So in CSI based DTC, the state estimate to calculate the subtangent flux lambda S star lambda S minus LCIS. LC is the commutating wave, lambda S is the estimate as Vs equal to RSIS plus d lambda S upon dt, and lambda is equal to integration Vs minus Rs dt at t equal to 3 by 2 p real part of j lambda S is star and equal to 3 by 2 p lambda dash is star sin theta, and this is the flux hologram of current vector. Here we have 3 0 current vector, and this is the 2 level your torque vector and the position of all 9 vector, 0 vector and 6 vector. So coming to line commutator inverter based DTC. Line commutator based DTC, the power factor is calculating with a constant power factor angle pi equal to 6 to 9 degree by setting T a star reactive. This provides the negative line voltage on just turn off the thyristor for safe commutation up to 150% of rated current. The power factor angle must take care of the overlap angle also, which is due to inductance. The power factor angle is given pi equal to gamma minus mu by 2, where gamma is the margin angle. And these are typically the block diagram of line commutator LCF pad drive. So coming to cycle converter based drive, the cycle converter based DTC is similar to the VSI scheme, and this scheme also power factor control is possible. However, the power factor is kept at unity for the most of the operation. So at very low speed, the field current is kept constant, high quick control is applied, and in similar manner, matrix converter based DTC also shown. So this is typically the cycle converter pad. This is your director control, and this is your matrix converter based director. And this is the modeling of DTC, the rotor reference frame. The cosmetic equation is phi SD phi SQ, USD USQ, UF 00, and then we have a complete matrix in ISD ISQ, IF, IRD ISQ. Then your G matrix d upon dt of current like ISD ISQ, IF, IRD IF, and then the torque, developed torque T equal to N in bracket pi alpha S alpha H beta minus pi S beta IL S alpha equal to NP in bracket pi SD ISQ minus pi SQ pi SD, and this is the steady state vector graph for synchronous from which equation are derived, and pi SD and pi SQ can be written pi SD equal to LM IF plus LST pi SD, that is pi S cos 10 delta ISM, and pi SQ equal to LS QISQ, that is pi S into sin delta, and the torque is expressed as T equal to NP in bracket LM TIF pi S upon LST sin delta LSM plus LSD minus LSQ upon 2 LSD LSM pi S square sin 2 delta F. The first part is the electromagnetic torque of synchronous motor, and the second part of electronic torque. So coming to modeling of your DTC for synchronous motor, so neglecting the hysteresis leakage inductance LRS, the main electromagnetic torque is the cross product of the hysteresis flux linkage vector and the rotor flux linkage vector. The main electromagnetic torque can be modulated quickly through first torque angle delta some change by controlling the flux vector, which is done by switching the appropriate voltage space vector. And the basic DTC block diagram for the typically VSI pad drive with the 3-step torque and 2-step torque, and of course here we have field current with the torque and flux estimation reference field current. So coming to now the error between the reference torque T star and the estimated torque is the input to the 3-level stage controller, and the error between the reference flux pi S star and the estimated flux is the impact of 2 level, and the rules for flux and C pi equal to 1 and 0, pi S minus pi star minus pi S is greater than psi eta, or 0 pi S star minus pi S is less than minus eta. And the rule for torque magnitude stage control CT equal to 1, 0 minus 1, T minus TL equal to greater than eta, or equal T equal to T star equal to E, T minus TL less than minus eta. That are the error between the, and this is a vector graph assuming hysteresis flux linkage shown for empty coordinates shown here. So now coming to basic DTC of the hysteresis flux vector in hysteresis flux linkage reference frame in empty coordinate can be written pi SM pi ST cos delta SM sin delta SM minus delta cos delta function of psi SD psi SQ equal to LSD ISM plus LMD IFM LSD IST LMD and equal to pi S0. So here LMD LMQ are the D axis magnetizing influences, and DQ axis current can be written as DI bracket cos that is 1 minus sin delta, cos delta, ISM, IS, and from previous equation, IST equal to minus LMQ upon LSQ IFT and T equal to NP IST IST, and total field current is IF equal to under IFM square IFT square equal to IFM square plus LSQ 1 LMQ IST square. And assuming ISM 0 and considering LSQ equal to LMQ, you can get the reference field current IF star equal to under IFM square IFT square equal to under IS upon LMD square plus T star upon LS ISQ square. Coming to sensor topology for DTC for synchronous motor drive. This is typically for voltage source inverter pad, your T reactive and with the sensorless speed position we estimate from sensor voltage current. This is for typically current source inverter pad drive, sensorless control. Then this is your cycle converter DTC for sensorless control, and this is your matrix converter sensorless. Now coming to case study, power quality improvement in for synchronous motor drive. So power quality is the quality of the voltage including its frequency and resulting current that are measured in grid distribution system or any other system. Power quality is a relative term with respect to the sensitivity of a device, equipment or system. So therefore any power problem manifested in voltage, current or frequency deviation that results in failure of means operation of utility or the end user equipment can be treated as power quality problem. Now there is a power quality standard IEEE standard IEEE 519 standard established in 1990 as a recommended practice and command for harmonic control in electrical power system, giving the limit 10, later on revised in 92 and IC 61000 and then further revised in 2014 IC 61000. Magnetic equipment have been categorized in 4 groups, class A, B, C, D for the purpose of harmonic current limit, and another standard of IEEE 1531 issued in 2000 gives the necessary guideline for use of shunt harmonic filter by low voltage electric power system, and this is a current distortion limit for general distribution say 120 to 69 kV IEEE 519. And you can see here main observation is total demand distortions will not be more than 5% if our source impedance is less than 5%, that is current short circuit level more than 20. And if you have a short circuit impedance very low, you can allow little higher harmonic so that voltage are distorted even of other load. This is for the distortion corresponding to high voltage system. So there is a more stringent limit of total demand distortion only of 2.5 or 1% for I. This IC 61000. This is classified with as a function of for harmonics as a maximum permissible harmonic current. So coming to classification of topology, LCFAD synchronous motor topology with the passive tune filter, multiple pulse converter, then active filter, rectifier chopper, and hybrid several combination of possible for active. The classification of topology in LCFAD drive. So many efforts have been made to improve the power quality as per the standard norms using a passive and active wave shaping technique. And the passive wave shaping technique usually have tune filter, but the filters cannot be designed for all harmonics. However, active filters becomes expensive if designed for a number of harmonics. Therefore, the hybrid wave shaping methods and some other passive topology can be thought of as a feasible solution, and the passive wave shaping topology can further be classified as passive tune filter or multiple AC/DC converter based topology, and active wave shaping topology can be classified as active filters and rectifier chopper based. So the thyristor converter pad, line commutator inverter pad, synchronous motor drive and diode rectifier chopper pad LCI drive have dual relation to each other in circuit and property. Therefore, parallel tune passive filter can be used with the thyristor based converter, where the series tuned passive filter can be used for diode rectifier with the capacitor filter for harmonic current compensation. Now coming to conventional passive wave shaping tuned filter topology, the tuned passive filter can also be used as a control and control multipulse converters, and in case of control converter, the passive filter reduces the notches in the input voltage waveform because of the commutation overlap and provides the reactive power required by the converter. So the reduction in TAD of AC mains current, improve power factor, partial load, and reduce magnetic rating are some of the advantage of passive tuned filters in case of uncontrolled converter. So however, these filters are quite bulky with a high volume and have reasonable losses which reduce overall efficiency of the complete system. So coming to multiple AC/DC converter based topology, the converters having more than 6 step in AC current are considered under multiple category, and they provide more than 6 pulses of DC per cycle from AC input current, and bridge rectifier is the basic building block of AC/DC conversion in multiple topology. However, the full wave and half wave rectifiers are also used for up to 120 kilowatt rating. Coming to multiple AC/DC converter, so phase shifting transformer is used to drive the multi-phase supply from 3-phase AC mains using a different combination of transformer winding, star, delta, zigzag, or polygon, etc. The advantage of multi-pulse topology, the performance parameters such as total harmonic distribution of AC mains current and ripple factor of output DC voltage improve simultaneously. So the improvement in the is independent of supply frequency variation, unlike the passive filter, and minimal or no control required as diodes or thyristors are mainly used, and cost-effective, maintenance-free, and this is the classification of topology. Multi-pulse converter, unidirectional like isolated, non-isolated, and bidirectional like isolated, non-isolated, and with the different pulses like 12, 18, 24, 36, 48 pulses with a star, delta, zigzag, polygon, hexagon, T-connected transformer. So now classification of this, the unidirectional and multi-pulse converter are developed using diode rectifiers and transformers, circuit configuration in isolated, non-isolated, and bidirectional multi-level converters are developed using thyristor spatial arrangement of magnetic through auto multi-winding transformers and interface transformer, tap reactor, and additional thyristor and capacitor with the concept of multiplication to obtain a higher number of pulses. So non-isolated multi-pulse converter, these transformers are basically output transformers with any one of the polygon, star, delta, polygon, hexagon, T, and zigzag, and these transformers use the inherent phase shift between the two windings using any of the following connections: star, delta, star, double star, polygon, action, delta, hexagon, T, and zigzag. Now coming to improve power quality converter, so is provided the reduced harmonic current, high power factor, low electromagnetic radio input, well regulated and good quality DC output, reading from the fraction of watt to megawatt power, large number of applications. Coming to schemes for power quality improvement in synchronous motor drive. So we have here the typically boost converter for single phase and then VSI. But in synchronous motor drive, we have a filter with the diode and then LC filter on DC link and with the single phase source. Then we have a typically the circuit of boost converter with the VSI, and then the bidirectional boost converter, voltage source converter with VSI. Then we have a both side 3-phase VSI for motor side as well as, and then we have improved quality boost converter with VSI, and we have a 3-phase synchronous motor drive with the current source inverter. On both the sides, typically IGBT based series diode or GTO based with the capacitive filter on both the sides. Coming to design of multi-pulse AC/DC converter for line commuted synchronous motor drive. So design of multi-pulse converters for LCI fed synchronous motor drive. The minimum order of harmonics in n pulse converter is nk plus 1, where k is the positive integer, n is the number of rectification pulses per cycle of the fundamental voltage, and the phase shift required for a converter having x number of 6 pulse converters is 60 degree on x, and the negative sequence voltage and currents are shifted in opposite sense to positive sequence value. And this is typically a 6 pulse converter with passive filter. So we have passive filter on typically on supply side with distortion, and then your thyristor converter with proper control of LCI. Then we have diode rectifier with the universal power flow diode rectifier with the buck converter. That's also for typically for isolate topology for 6 pulse converter. Then typically again diode rectifier with your 6 pulse topology, and these are the TAD, of course, supply TAD 21%. The 12 pulse AC/DC can require a phase shift of 30 degree. It can be achieved by two configuration using isolated star, delta transformer combination, or using a isolated star zigzag transformer. The turns ratio for star zigzag 1 and zigzag 2 transformer given as n3 upon n2 plus n3 0.366 and n1 upon n2 plus n3 1.41, where n1 is the number of turns per phase star winding, and 2 and 3 are the number of turns of zigzag winding. And this is the 12 pulse converter with, of course, buck converter, reading line converter inverter, and this is another combination of 12 pulse with the star zigzag. This is your 12 pulse again with the you can call the your hexagon with 12 pulse converter, and the TAD here, of course, of less than 6%. So now coming to 18 transformer design for isolated 18 pulse AC/DC converter configuration. Requires phase shift of plus 20 degree 0 or minus 20, each achieved by use of 2 zigzag and star winding in the secondary side of the transformer. The turns ratio of star zigzag 1 zigzag transform at the 20 degree and minus 20 degree phase shift respectively, and n3 upon n2 plus n3 0.227 and n1 upon n2 1.959, where n1 is the number of turns on primary page star and n2 and 3 are number of turns in zigzag band. And they typically 18 pulse converter with the diode rectifier with the buck converter feeding the LC die to drive the current source. And this is another configuration of your typically of 18 pulse topology with the buck converter, and the TAD here is considered less than 5%. You can see at light load as well, even your isolated and non-isolated both topology. So coming to 24 pulse converter, the 24 pulse HD is going to require minus 15 0 plus 15 plus 30 between the 4 sets of, and it is achieved use of 2 zigzags, star winding and a delta winding in the secondary, and the turns ratio of star zigzag 1 zigzag to transform void the plus minus 15 degree phase shift respectively, and size similar to 12 pulse converter phase shift transformer. And this is typically 24 pulse converter with a buck converter driving a current source forward. This is another topology of 12 pulse with extended. This is another topology of 12 pulse, with the pulse doubling. And TAD here of course comes around less than 3.7% and 2%. And this is a comparison of the different multipulse converter, how really the TAD and total magnetic ratings are there. Now coming to solved problems. Example 1, a vector control synchronous motor with data Vn equal to 660 line voltage RMS star connection, In equal to 353.55 RMS, Rs equal to 0.016 ohms, LD equal to 2 L cube, 0.0056 Henry, LS1 L equal to 0.1 LD, and at 50 F equal to 60 Hz, pole pairs 2, and rated flux is 1.4068 Weber for a leading power factor angle phi equal to minus 12 degree. Calculate the IDIQ IF for rated current. So IS equal to IN under root 2, that is 500 by root 2 into 2, 500 RPM, and IQ is approximately equal to IS cos delta plus phi 1, and ILD IQ equal to lambda S or sin delta. So for putting the value, we get the delta equal to 39 degree, and IQ putting up IS cos delta plus phi, that comes 314.66. ID comes with the formula minus S cos delta, that comes minus 388.57. IF equal to lambda D minus LD, IQ upon LD, that comes 648.78 ampere. Coming to second example, a vector control synchronous drive with Vn equal to 660 volt, line voltage RMS, star connection. In equal to 353.55 RMS, Rs equal to 0.016, LD equal to L 0.0056, LS1 equal to 0.1 LD, for 50 F equal to 50 Hz, pole by 2, set like 1.4068 Weber for the leading power factor angle minus 12 degree, determine the electromagnetic torque. So IS equal to IS root 2, that comes 500, T equal to 3 by 2 P real part of J lambda S IS star, that comes to be like a T equal to 3 by 2 P lambda S IS cos phi 1, putting a value it comes 2063.83 Newton meter. Coming to example 3, a 40 kV at 220 volt 6 pole synchronous motor operating at 60 Hz with the field current of 2.64 ampere, and which produce an open circuit voltage of 220 volt if the motor is loaded to rated torque and operating under field oriented control system as ID equal to 0. Calculate IQ. Solution: the field inductance AF equal to root 2 AF upon omega IF, putting a value it comes 0.18 Henry, and the rated torque is given T rated P rated upon this, so it comes at 318.47 Newton meter, and from LF equal to root EF upon omega IF, so it comes 0.18 Henry, and torque rated is T rated equal to P rated upon omega from 318.47, and thus T reference is T rated 318, so IQ equal to 2 by 3, 2 upon 4, T reference upon LF into IF into IF reference, so it comes 148.92 ampere. Example 4, a 3-phase 125 kilowatt for 1550 Hz 4 pole synchronous motor is operated in field under control mode. The motor has a synchronous reactance of 0.95 per unit and ampere field no load current, a voltage of 16 ampere. The motor is controlled in director control mode at a speed of 100 rpm and 0.8 times the rated torque. Calculate the reference torque, reference flux, motor line voltage, rated frequency, and the output power. Coming to the solution, the motor is to run at 1100 rpm and 0.8 times the rated torque. So the torque is calculated T rate P rate upon omega rated rate, that comes 795.71 and T reference 0.8 rated, that's 636.61 Newton meter. Then the motor is controlled below base speed, therefore reference plug lambda is V rated upon E rated 0.76 Weber, and from relation to E rated upon the V nu upon omega E nu. So motor terminal voltage at 11, that is omega E nu 33.66 Hz, 4 volt machine, and V nu equal to 304.22 volt, and stereo frequency is omega E reference, that's 36.6 Hz, and equal to output power T reference omega, that is 73.35 kilowatt. Now coming to example 5, 45 kVA 220 volt 6 pole synchronous motor operating at 60 Hz with a field current of 2.84 ampere. The motor is loaded to rated torque and operating under field frontal control such that ID equal to 0. Calculate the motor phase current IE, IB, IC as well as the per unit value and the armature current, and the motor terminal voltage is assume theta m equal to 0 at t equal to 0. That's a constant rotor. Direct axis is aligned with the phase A at t equal to 0. The axis equal to 0.836 per unit. So for solution we have LF equal to root 2 F upon omega V IF. So from this putting value, LF comes by 0.168 Henry. T rated equal to P rated upon omega rated, it comes 358 Newton meter by setting T, and I reference 2.84. So we can get IQ equal to 2 by 3, 2 upon poles, T reference upon IF, IF reference, and putting value it comes 167 ampere. So now theta m equal to omega t. So transformation of dq variable to ABC results in ID equal to 0, omega equal to 1, 377, I equal to ID cos dt minus IQ, that is minus 167 sin omega et equal to minus root 2 118 sin omega et, IB minus root 2 118 sin omega t minus 120 ampere, IC equal to root 2 118 sin omega t plus 120 ampere. So armature current is 118 ampere and the machine base current equal to I base equal to V rate than root 3 BS, that comes to 118 ampere. Thus the per unit current is your 120. And coming to B, from phasor diagram, the terminal voltage is VA star equal to JXS IA plus EF, LF equal to root 2 EF upon omega EF. So EF comes a 127. So base impedance of the machine is equal to Z base equal to V base is per P base. So it comes 1.076 ohm, and the synchronous reactance of 0.836 is equal to X is equal to 0.850, it comes 0.899 ohm, and the thermal voltage is VA to JXS IA plus EF, putting value from 65 at the angle of 129.9 degree, and therefore VA 287 1.3 per unit. Coming to example 6, a 3-phase 120 kilowatt 440 50 Hz 4 pole synchronous motor is operated in field torque control mode. The motor has a synchronous reactance of 0.95 per unit and ampere field. No load current AFL at 15 ampere. The motor is controlled direct torque control at a speed of 1200 rpm at 0.5 times the rated torque. Calculate the reference torque and reference speed. So the solution, the motor is run at 1200 rpm, speed 0.5 times the rated torque, and the rated torque is T rated, P rated, that's come putting value 764.33 Newton meter. Therefore reference torque is 0.5 T rated, 382.16 Newton meter, and the speed control in below base speed of lambda is V rated upon omega, that comes 0.80 per Weber. Coming to example 7, a 3-phase 1100 kilowatt 6600 volt 6 pole 60 Hz star connected one field synchronous motor has the following parameter: XM equal to 30, XL equal to 6 ohm, RS equal to 1.2 ohm, RF equal to 5 ohm, and equal to 2. The machine is controlled from variable frequency source. K by F ratio maintain constant up to base. Calculate the armature current, torque angle, torque factor at full torque, half the rated speed and rated field current, and the armature current, torque factor at the half speed, half the rated speed, half the rated torque, and the rated current, and the torque and field current for the rated armature 1500, and the unity power factor in the constant N is given by NF root 2 upon 3N, where the NF are the number of turns in armature and field winding respectively. So coming to solution, synchronous speed equal to omega equal to pi f upon p, that comes 127.5, 125.7 radian per second, rated of p upon omega, it comes 8071 Newton meter, v equal to 6600 by root 2, so it comes 3810.5 volt, and I am equal to v upon the axis, so putting a value, it comes here 105.8 at the angle minus 90 degree. So since perfectly unity, so putting into relation, we get I is equal to 99 at below, and IF equal to IM minus IS, so it comes for 49.8 minus 133 degree, IF equal to XS upon X on N, it comes 86.94 ampere, and sin delta is P upon 3 VIF, IF, that comes 0.66 to result delta equal to 41.6 degree, and for the half the rate speed 600 rpm, the V by F is constant, so IM remains constant, so delta will remain the same, therefore for constant value of delta and IM, IS, the power factor also remains unchanged, thus the IS equal to 99 at the angle 0 and delta equal to 41.6 degree. Electrical power factor unity, and half the radiator torque is 4370.5 Newton meter from T equal to 3 XS upon omega IM IF sin delta, get from a sin delta equal to 0.3 for delta 0.94 is cos pi 30.4 and is sin pi 47.8, IS equal to 56.6 and cos pi equal to 0.5 full D. So since the operation is taking place at rated terminal voltage, rated current and unity power factor will by P equal to 1100 kilowatt, 1500 rpm, 147th, X equal to 1500, 1200, 36, 45 ohm, and IM equal to VS upon XS 84.68 ampere. I is equal to I sin V equal to minus IM plus I have cos delta, and I is cos pi equal to I sin delta, pi equal to 0, I have cos delta 84.5, I have sin delta 99, therefore IF is 130 ampere. Coming to example 8, a self-controlled or computed current source in motor drive, supply a 556 kilowatt 3-phase 6656 pole star connected motor with a 50 millihenry computing inductance, 81 ohm synchronous reactance, negative RS, anti-unity power factor. The field current is controlled to keep the constant flux up to basic speed and the constant commutation lead angle control. This drive is not operated above the basic speed and motor can never exceed the rated value. Calculate the commutation lead angle beta so that the minimum margin angle of 15 degrees available for all operating points. Power factor, torque, and DC link voltage with a fixed beta at the value of calculated above for the rated speed and rated armature current. Repeat the part second for 25% of rated armature. Also calculate the margin. Coming to solution, when the operation takes place at a constant flux except low speeds, the voltage frequency ratio remain constant, and with the commutation lead angle maintain at constant beta C. Mu and gamma depends only on ID and are independent of speed, hence the beta can be evaluated after using at 15 degree margin angle at the rated armature current. Rated armature current in motor of power input divided by root 3 line voltage into motor power factor. Rated armature current is power divided by root 2 in voltage, that's a 47.74. The speed 120 of high number of poles, it comes 1200, 126, 5.7 radian per second, equal to 6600 root 3, 3810.5 volt, omega equal to 371, omega LC 18.57, to one motor fed inverter higher is 47, and DC link current is root 3 to higher, that's 58.47 your ampere, and supply current is root 6 upon ID 45.6 ampere, cos beta equal C equal to cos 15 minus 2 omega LC ID into beta C comes 43 and mu equal to beta C minus gamma, that comes 28 degree. The power factor angle is pi equal to beta C minus 0.5 mu, that comes 29 degrees. So power factor is cos pi 0.37, PM equal to 3 VHI cos pi, that is 453.5 kilowatt, and that T equal to PM upon 543, so it comes 3600 3607.8 Newton meter, alpha equal to 180 minus beta C, that is 137. DC link voltage VT equal to root 3 root 6 upon 5 cos B cos alpha minus 3 upon 5 LCID, that comes minus 757.11 volt, and armature current is now 25% of ASL, so IS equal to 0.54 5.12, so IS 0.25 45 11.4 ampere, and ID equal to 14.62, cos gamma equal to cos beta plus 2 omega LC upon root 6 V ID, that's gamma comes 37.8 degree. So mu equal to beta C minus gamma, that is 5.2 degree, pi equal to beta C minus 0.5 mu, that is 40.2 4 degree. Power factor is cos pi, that 0.4. Power developed 3 VSIS cos pi equal to 99.24 kilowatt, and torque equal to power developed by omega, that is 1085.9. Additional code is 3 root 6 1 pi v cos alpha minus 3 upon pi omega LCID, that's minus 6782 volt. So coming to example 9, the page 6 kilowatt 3 phase for 15 line 50 Hz for pole star connected synchronous motor has a stator line resistance, winding resistance 0.5 ohm, access equal to 5 ohm, and rated field current of 2 ampere. The speed of the motor is controlled using indirect vector control scheme using field long voltage source inverter. The motor is controlled with constant flux below base speed and constant rated torque above base speed. Calculate the reference DQ component of stator current and starting torque is required rated. Reference DQ current component of stator current and stator frequency at half the rated speed and half the rated torque. So coming to solution, A motor produces rated open circuit VOC equal to 415 by root 3 and the field current of 2 amp. So that LF equal to VOC of IF comes 0.5395 Henry. T rated equal to rated upon omega T2 per 38.1 Newton meter, and IF equal to T reference equal to T rated. So IQ equal to by 3 1 volt T rated upon IF, that's 11.8 ampere, and VOC is omega E under LD ID square plus whole square L cube IQ square by root 2. So ID comes minus 1.027 mm. Therefore, source current ISID is IQ square by 2 under root 8.375 ampere. Coming to B part, if the base speed is reduced to half the rated, then omega E star upon omega rated 0.5 to be rated E star and torque is 0.5 rated. Therefore, armature current IA equal to T rated I on 3B, so it comes 4.173 ampere, and angle between IA VOC delta equal to minus tan inverse omega E star LSI upon V, that is minus 4.977 degree, and ID equal to root 2 IA cos delta 5.879 ampere, and IQ equal to root 2 IA sin delta 0.512 ampere. Therefore, stator frequency is omega T star equal to 2 IF, that 0.5, that is 157 radian per second. Coming to example 10, the 3 phase 6 kilowatt for 15 volt 50 Hz 4 pole star connected synchronous motor. Example 1 has a stator winding resistance 0.5, x equal to 5, field current of 2 ampere. Speed of the motor is controlled using the indirect vector control using field on BSI. The motor is controlled with constant flux below base speed and constant rated voltage above base speed. Motor speed required to raise 1.5 times the rated speed and half the rated torque. Calculate the DQ component of the stator current and stator frequency. Coming to solution, the speed is raised to 1.5 times the rated with half the rated torque. Then the motor will have constant voltage above the base speed. V star equal to V rated. Desired torque T star equal to 0.5 rated. The power is also constant. P equal to T star M star 0.75 P rated. So I equal to 0.75 I rated 6.255 ampere, and T proportional to 1 upon omega T upon I star read. So omega equal to 2 pi, that is 471.23 radian, and IA and VOC, the delta equal to tan inverse omega E LS IA upon VA, that is on minus 11.078 degree, and ID equal to root 2 IA cos delta, that come 8.681 ampere, and IQ equal to root 2 IA sin delta 1.699 ampere. These are the references which I have used for developing this lecture. Thank you.